In this video, we're going to talk about the different stages of a star's life, which is a process that we call stellar evolution. Now, where it begins is a large cloud of dust and gas. The gas is mainly hydrogen, but there's little other substances within the cloud. We call these molecular clouds. So molecule might imply small, but these molecular clouds are enormous. They're giant clouds of dust particles and hydrogen gas, and then some helium gas and some other things, mostly hydrogen gas. Because of gravity, eventually these large clouds are going to condense. They're going to get smaller. Gravity is going to pull them in together. And that's going to make the cloud more dense. As that happens, there will be pockets that develop that are even more dense than the average. And those denser pockets are going to collect themselves and fragment the cloud into a bunch of smaller clouds. Those smaller clouds will become protostars, so not quite stars, so the early stages of a star forming. So from a big cloud, you get fragmentation into smaller clouds. Those smaller clouds become protostars. So they're not quite stars yet, they're just small clouds of dust and gas that are being condensed by gravity. Gravity is continually pulling them in. And as that happens, the star will start to take shape. It will start to become a round ball of dust and gas when it originally was some amorphous shape, some random shape to it. Now, if that cloud is large enough, eventually the pressure is going to reach a point where the hydrogen will begin to fuse. Gravity will keep pulling it in closer and closer and closer together. The weight of that cloud will press the center to become the core of a star. Hydrogen will begin to fuse and it will begin to burn visible light like we see with the stars in the sky. Now, if it's too small, if it's fragmented into a piece, if the original molecular cloud is fragmented into a piece that's too small, it may not form a star. In that case, it will become what we call a brown dwarf. Now, sometimes you see these referred to as brown dwarf stars. If you define a star as having nuclear fusion in the core, then these are not technically stars. They're round balls of dust and gas. They look more like Jupiter than the sun. Now, once a star is born, it's got nuclear fusion happening in its core. It is going to be somewhere on the main sequence of an HR diagram. Now, on this picture here, there's a yellow line. This yellow line is called the zero-age main sequence. When a star is born from that original molecular cloud, it will appear somewhere along this line. And where it ends up will depend on what type of star it is. So if it's a type G star, it will appear right here on the zero-age main sequence line. A type B star will end up over here. Now, during its life cycle, the part of its life cycle on the main sequence, its mass isn't going to change very much. The energy that it's creating is only using a little bit of mass. Hydrogen is converting into helium, and a small fraction of that hydrogen's mass is converted into pure energy and released as light. In fact, it's only about 0.7%. So its mass doesn't change very much, and that means that it's not going to drift too much while it's burning hydrogen in its core. So there's some scattering that happens off of the zero-age main sequence, but it roughly stays in this same place on this main sequence part of the HR diagram. Okay. Now, how long will it last in this stage of its life? So it's born, it appears on the yellow line. It might drift a little bit off of that line, but it will roughly stay in the same area of the diagram. So a type G star may start here, may drift over to here, but it's going to stick around in this vicinity of the HR diagram. How long will it live there, what we call its main sequence lifetime, will depend on where it started. So stars that are down here, the coolest stars, the type M stars, they actually live the longest lives on the main sequence. They can be there for hundreds of billions of years. Whereas type O stars, they actually go through their main sequence lives much, much faster. They might only be on the main sequence for 1 million years before leaving. And so lifetime of a star depends on where it falls along this zero-age main sequence. How about our sun? Well, our sun has a main sequence lifetime estimated to be 10 billion years. Right now, it's around 5 billion years. So we're just rounding these numbers here. But about 10 billion years, and it's about 5 billion years old. That makes it a middle-aged star. So a while back, we talked about the sun and how it's sort of average in a lot of ways. It's also average in terms of its age. It's right in the middle of its life. Now, we can think about the lifetime of stars in a lot of different ways, but one of the more interesting ways to think about the lifetime of a star is how it affects evolution. If you're interested in how life has evolved on the Earth, the fact that we live around a star that has a lifespan of billions of years was really critical because it requires billions of years for evolution to happen. At least evolution, the way it happened on Earth, requires billions of years. So could life have developed on a type O star or a type B star? According to what we know, probably not. Those stars don't live on the main sequence for long enough. Now, why is it important that it's on the main sequence? Well, if it's not on the main sequence, what we'll learn is that the properties of the star can vary pretty wildly, meaning it's not very stable. And it can grow in size and change in temperature, and the radiation that's coming off of it can change dramatically. If you're thinking about life evolving near that star, those are not good things. You want life to evolve, at least how we understand how life evolves, in a very stable environment that stays stable for billions of years. Luckily, we have that in the sun, and we will hopefully have that to continue for at least another 5 billion or so years. Okay, but eventually, all stars will leave the main sequence, and that will happen when they've run out of hydrogen in their cores. There's a finite amount of hydrogen in the core. Eventually, it will all get converted into helium, and when that happens, it can no longer produce helium through that reaction, the hydrogen burning reaction, the proton-proton chain. That can't happen anymore. Now think about that in terms of hydrostatic equilibrium. Hydrostatic equilibrium was the balance between an internal pressure and gravity. So gravity is pushing in, and that internal pressure is pushing back out. Well, fusion of hydrogen was that internal pressure. Once hydrogen is gone, that can't push back anymore. So the core immediately will collapse. And when the core collapses, the hydrogen that was just around the core will start to burn. So if you imagine this is the core and this is outside of the core, when the core collapses, there will be a helium core remaining because all the core was hydrogen that had been converted into helium, so all you have left is helium. But around that, when the core collapses, the hydrogen around it will start to heat up and increase in pressure, and it will start burning. And so you'll get a hydrogen burning shell around the helium core. And that is what will next push back against gravity. Okay, so you think about it in terms of hydrostatic equilibrium. You initially have gravity balanced by hydrogen burning in the core. When that runs out, the core collapses, gravity wins temporarily, and then hydrogen starts burning in the shell around the core, and that pushes back against gravity. And when that happens, the star actually expands in size dramatically, and it becomes either a giant or a supergiant. Big increase in luminosity as well, so it becomes a much brighter star. Okay. For a star like the sun, it will end up becoming a red giant, and so the sun will go through a red giant phase. Now we can see a red giant in our night sky. The star Betelgeuse, which I believe we've referred to a few times, is a red giant. It's actually a supergiant It's in the constellation Orion, and you can see its properties over here. So it's a star that's much more massive than the Sun, 16 times to be exact. Its radius is thousands times bigger than the Sun. Its temperature is cooler, right? So it's gone from essentially a yellow star to a red star. So it's cooled in temperature. It's become redder. Its core temperature has gone up due to the increase in pressure. Its luminosity is much, much greater. But because it's blown up to such a big size, it's not very dense. That means the outer parts of it have gotten way, way, way less dense. The star has expanded to such a big size. But in terms of lifetime, the Sun, 4,500 million years, which would be about 4.5 billion. Betelgeuse, only 10 million years old. So it's a much more massive star, and that meant it went through its evolution a lot faster than the Sun did, or the Sun will. For its size comparison, you can see here in the picture, size of the star is this line here. The size of Earth's orbit is here. So if we were orbiting around Betelgeuse at the same distance we're orbiting around the Sun, we'd actually be inside the star. And that would be even true for Jupiter's orbit. Now, if we look at where Betelgeuse goes on this diagram, we can compare it to where the Sun will go based on the diagram, what it shows for different size stars. So a 1 solar mass star is here. That's like the Sun. It will leave the main sequence here and take a path up here to become a red giant, right? So it's decreasing in temperature, increasing in luminosity on the HR diagram. So becoming redder and brighter and also bigger. That's what happens when it runs out of hydrogen in its core. But for a star like Betelgeuse, which was 16 times more massive, that puts it farther and farther up here. All right, so the Sun's path is second from the bottom, this one. Betelgeuse would be similar to the top path. It would go up here. So again, it becomes a red giant, but because it started out so much bigger than the Sun, it actually is a red supergiant and ends up here. Right. Now, there's more to the evolution of stars. We've talked about the stages of evolution up to leaving the main sequence. For the rest, the remainder, we'll have to get into that in later videos. So we'll stop here for now. We've covered from the birth of a star from a molecular cloud through the main sequence and now leaving the main sequence. What happens next depends on the initial mass of the star, and we'll get into that more in the later video.